welcome to the NASA Hyperwall. My name is John Haynes. I'm Program Manager for Health and Air Quality Applications in the NASA Applied Sciences Program at headquarters in Washington. And over the next 14 minutes or so, I want to give you an overview of what we do in air quality applications at NASA and in the Earth Science Division as a whole. Some people would say this will be a 30,000-foot overview of the program, but at NASA we say it's a several hundred-kilometer high overview of the program because this is where, for us, it all begins. The constellation of 18 Earth satellites and sensors in low Earth orbit, continuously monitoring Earth's weather, climate, and environment for research and applications purposes. Now, this constellation represents the largest non-military Earth-observing constellation in the world. It represents an investment of $2 billion, that's billion with a B, dollars per year of American taxpayer money. And it also makes NASA the largest contributing federal agency to the United States Global Change Research Program, which is a consortium of 13 federal agencies that either have a mission related to climate change or a mission that may be impacted by climate change. So when you're looking at this constellation, I just want to point out a few ones that you have probably already heard several times in talks over the past week, but you'll hear again today. First of all, we'll point out our flagship satellites. You see Aqua coming around the South Pole there. Aqua it's a flagship because it has multiple sensors on board, primarily looking at the world's oceans, including the MODIS sensor on board Aqua. MODIS stands for the Moderate Resolution Imaging Spectroradiometer. Quite a mouthful. You see why we use acronyms at NASA. But MODIS is very important. MODIS looks at the Earth in over 30 different wavelengths of the electromagnetic spectrum. That way we get everything from ocean temperature, land surface temperature, vegetation greenness, aerosol optical depth, the loading of particulate matter in the atmosphere. We can look in the infrared and look at wildfires across the world. It's an extremely important workhorse for the program. If we zoom back into Earth, you'll also see our Terra flagship. MODIS is also on Terra. Terra mainly looking at the Earth's lithosphere. And then you also have Aura, the Aura flagship with multiple sensors on board, looking mainly at atmospheric composition of the Earth. One of the most important sensors on board Aura is the ozone monitoring instrument, OMI. And if you can guess, what do you think OMI looks at? Ozone, it wasn't a trick question. But it looks at a lot more than ozone as well. It also looks at nitrogen dioxide, sulfur dioxide. We've been observing, actually, ozone from space at NASA since the late 1970s. That's how we discovered the Antarctic ozone hole that now OMI is showing is healing, actually, thanks to the Montreal Protocol banning CFCs back in the mid-1980s. And also, OMI, I want to point out, is very important because it's an international contribution. We could not have the robust Earth science constellation we have without our international partners. OMI is a contribution from the Royal Dutch Meteorological Institute, but many of our other satellites are from in partnership with international agencies as well. The Global Precipitation Mission, GPM, which, as its name suggests, looks at rainfall, snowfall rates, and totals across the world, is in partnership with JAXA, the Japanese space agency. Calypso, which you'll see Calypso come around in just a second. Calypso is an on-orbit LiDAR. Basically, you can think of it as a laser radar in space, looking at aerosols in 3 dimensions across the planet. And that is a contribution from the French space agency, CNES. So let's go to the next slide. And on this slide, we're going to take a look at those NO2, those nitrogen dioxide observations from OMI on board Aura. Where does NO2 come from? Well, it comes from some natural places, such as biomass burning of forests, wildfires, agricultural burning. But it also comes from industrial sources and also vehicular emissions. So when you look at NO2 levels across the world from OMI, and this is through the year 2014 into 2015, we can find some interesting features. When you're talking about that agricultural slash burning and burning off of fallow fields, you can look at the Congolese rainforest and see when those agricultural activities are occurring because nitrogen dioxide levels really spike. You also, unfortunately, will see that coming up at times in the Amazon rainforest as slash and burn agriculture is going on there as well. You can see the very highly industrialized areas of the world glowing. The eastern megalopolis of the United States, Los Angeles, San Francisco glow, the industrial Ruhr Valley in Germany, and all the rest of the major cities in Europe. You can also see the large cities in China and Japan glowing with their industrial emissions. You can also point out some very specific industrial activities that are going on. This glowing in South Africa is diamond mining going on in South Africa and the emissions coming from that. These glowing dots in Chile are copper smelting plants. So you can pick out very particular emissions across the world. Some areas you'll see that nitrogen dioxide levels are increasing, particularly in the developing world as they become more industrialized, in India and China. But in other areas of the world, they're decreasing. So let's go to the next slide. And we'll zoom in on the United States. And this is a good news story. And we like to tell good news stories. If I was to come up to an average person on the street, probably not y'all, because y'all are at HU scientists, but if you came up to an average person on the street and said, is air quality better or worse than when you were a child? Most people would probably say worse, because people tend to think everything's always getting worse. But I've got a good news story to tell you. The air quality in the United States is the best it's ever been in the modern industrial age. That is not fake news. That is real news. Tell everybody. And why is that? It's because of all the hard work we've all done. The Clean Air Act regulations, new technologies to help scrub the pollution coming out of industrial plants and coal plants, increasing vehicular mileage regulations, those CAFE standards to make our cars more efficient. Also, the huge revolution in the United States in using more natural gas rather than coal and natural gas. It's a much cleaner burning fossil fuel. So over the past 10 years, we've seen a reduction of 20, 30, sometimes 40% of nitrogen dioxide in cities across the United States. In fact, this news was highlighted in the 2016 EPA Air Trends Report. For the first time, they used satellite data as part of their Air Trends Report in showing the improvement across the United States. It was also touted on Discovery News by President Obama in 2016. Because this, again, is a good news story. When we announced these results on CNN, the CNN chyron at the bottom said, air quality is improving in the United States, ? But this is why we want to get this story out, because people say, oh, what all these regulations, what do they do? What do they do for us? These are what they do for us, and we need to tell people that. So you can, again, look at the United States just between 2005 and 2009 when you're looking at different cities like Los Angeles, like Chicago, looking over here in Atlanta, Tampa, and you can see the huge reductions that are going on. So let's go to the next slide. So what we're going to look at here is a zoom-in image of the city-state of Singapore at the end of the Malay Peninsula. And what we wanted to do here is to show a comparison in a very good air quality day and a very bad air quality day. So as the slide goes back and forth, what you'll see when it's a clear day is a very clear day in May in 2015 in Singapore, where this is actually a visible image from MODIS, again, that workhorse for us. And then when it slides, so when you're sliding back, you're seeing this clear air day. You're just seeing the cumulus clouds. It's a beautiful day. And we're comparing it to that Calypso LiDAR data at the bottom. Remember, that's the one that gives us that three-dimensional look of aerosols in the atmosphere. So you see there's really not much going on because it's a clear day when MODIS is looking in 3 dimensions of the atmosphere above Singapore. But then, just a few months later, we had huge wildfires raging in Indonesia, and all that smoke was being evicted across the city-state of Singapore. You can see the smoke in the visible for MODIS, but you can really see it here on Calypso as it picks up these curtains of smoke in the atmosphere, both at the mid-levels and also near the ground where we breathe. In fact, during this time in Singapore, they had to cancel outdoor activities, they had to close schools, people were restricted from doing any outside exercising or anything like that because the air quality level was so hazardous. Let's go to the next slide. So we're going to zoom in now on the country of Iceland. Particularly, we're looking at imaging from 2010, both from a geostationary satellite of the European Union and also, again, from Calypso, because we're looking at a volcanic eruption in 2010 in Iceland. This was the eruption of the volcano that had 21 letters in its name that I will not attempt to pronounce. We just like calling it E21. But this eruption, many of you probably remember from the news, and you probably particularly remember it if you were in Europe at the time or in the United States trying to get to Europe, because it shut down all air traffic across the Atlantic Ocean. Now, why is that? Why is volcanic ash so important and such a hazard to air traffic? Volcanic ash is basically ground glass in a way. And when you're in an airline and you fly through a volcanic ash cloud, you're ingesting all of that ground glass into the jet turbine engines, sandblasting them anyway. Plus, the heat in the jet turbine is melting that ash, so it's basically becoming blown spun glass to the engines. And this can lead to a very bad day of flying. And in fact, this is not just hypothetical. These, unfortunately, have happened incidences with aircraft over the past 30 or 40 years. In 1982, a 747 of British Airways was en route from London to Auckland, New Zealand, and ran into a volcanic ash cloud from a volcano in Indonesia. They lost all 4 engines, and they began, because gravity still works, to descend toward the ground in a not good fashion. The cabin is filling with the sulfur dioxide smoky smell. You're certainly having the oxygen mask come down. You can only imagine what the cabin was like. And in probably the best British understatement ever, the captain comes on And he says, ladies and gentlemen, this is your captain speaking. We have a small problem. We have lost all 4 of our engines. We are doing our damnedest to get them back on. I trust you're not in too much distress. I would have been in distress. Luckily, they were able to get one of the engines restarted before a crash occurred and made an emergency landing in Jakarta. Just a few years later, 1989, same thing happened with a KLM 747 flying across Alaska. Mount Redoubt had erupted. They ran into the volcanic ash cloud, lost all 4 engines. Luckily, just before a terrible accident occurred, they got one of them restarted, and they landed in an emergency landing fashion in Anchorage, Alaska. After those incidences, the world said, we have to come up with a new system because we're not accurately being able to locate where these eruptions are occurring and where these volcanic ash clouds are going. So the world came together and formed Volcanic Ash Advisory Centers, known as VACs, and they gave responsibility in different regions of the world to different meteorological agencies in the world to monitor volcanoes, to develop modeling to see how that volcanic ash will be transported over the next few days. So that way we can safely block off pieces of the airspace across the world so planes don't interact with these volcanic ash clouds. In the United States, the Volcanic Ash Advisory Centers, we have 2 of them, run by the National Oceanic and Atmospheric Administration. One is in Washington, D.C. The other one is in Alaska, because Alaska has over 70 active volcanoes itself. They need their own center. The one in Washington, D.C. has the largest area in the world to cover, everything across the United States, all the way down to the Andes of South America, and all the way over to Guam. So we work very closely with the Volcanic Ash Advisory Centers, not only with NOAA, but worldwide, to get NASA's information into their modeling to be able to better monitor and track these volcanic pollutants. Not only with the Calypso data that you see here on this image, looking at where that volcanic ash is in 3 dimensions, but going right back to OMI again, the ozone monitoring instrument. Volcanic ash is chock full of sulfur dioxide. And like I mentioned earlier, OMI not only looks at ozone, it looks at nitrogen dioxide and sulfur dioxide. We can look at sulfur dioxide as a proxy for where volcanic ash is, because where there's one, there's the other. So we actually, during this eruption, we were able to work very closely, us and NOAA, with the Met Office in London, who has actually control over this area of the North Atlantic, to help get them that information from OMI so that they were better and more accurately able to predict where the volcanic ash from this Icelandic eruption was going to go, where it was currently located. That way, they, instead of having to block off that huge area of airspace when they didn't have this information to be on the safe side, they were able to tailor that. So we were able to start flights again, flying across the Atlantic and get our air traffic going again. So with that said, I'm going to stop there, and I have about a minute, I guess, left for any questions. But I appreciate your time and hope you have a wonderful rest of your stay here at AGU and in the Big Easy. Thanks a lot.